Hello, everyone, and welcome to our webinar today on Autonomous Cars of the Future Will Rely on 5G, but How Will We Get There?, presented by Qualcomm. I'm Tara Seals, contributor to Fierce Telecom, and I'll be moderating the webinar today. Let me introduce our speakers. Today we have Nakul Duggal, who is the Vice President of Product Management for the Automotive Business Unit at Qualcomm, and also George Tsirtsis, who is the Senior Director of Technology at Qualcomm. You can read their full bios on the left-hand side of your window there. And just I want to go over a couple of housekeeping notes before we begin. If you'd like to download the slide deck, you can do that. You just need to click the Files button at the lower left of your screen. Also, the webinar is going to be recorded, and that will be available on demand within 24 hours after we finish our event. And also, after the speakers are done with their presentations, we'll have a Q&A session. You can submit your questions during or after the presentations by clicking the Q&A button on the lower left corner of the screen, and we will get to as many of those as we possibly can. And with that, I'll turn it over to our speakers. Nakul, please go ahead.
Thank you very much, Tara. Good morning, everybody. This is Nakul Duggal at Qualcomm. Thanks very much for your time this morning. There is a lot going on at Qualcomm in the areas of automotive, and I'll speak to you a little bit about the communications aspect of what we are doing in this space. So this is a fascinating time in automotive. We are seeing unprecedented innovation, unprecedented growth in terms of every facet of the technology that goes into our cars, from electric vehicles to intelligently connected vehicles, the transitions in ride sharing, and then of course autonomy. We'll spend a lot of time today talking about our vision for vehicle-to-X services, whether those are talking to other cars, talking to pedestrians, infrastructure, and the network. And we believe that on the path to autonomy, vehicle-to-X services are going to play a role that will be complementary and extremely important in the future. At Qualcomm, our view for the car of the future is that it will be connected to the cloud at all times. We'll share with you, between George and I today, our vision around 5G and the path to get there in terms of what communications for the car means. But really what this means is not only will you have higher data rates and ubiquitous coverage, but you will have very low latency. You will have security, a very large number of connections that will all be serviced through today's 4G networks and then evolving to 5G networks. The second piece that we believe is an extremely important facet of autonomy is mapping and positioning. The ability to localize and know exactly where you are to the precision of centimeters is something that will be an extremely important part of autonomy, and that is something that is being powered by our technology through various types of advances, not only in positioning, which is obviously extremely important, but abilities like dead reckoning, visual inertial odometry, which allows you to combine camera information with location information, and of course cloud-based assistance, which again takes you back to 5G connection. And then finally, we believe that onboard intelligence, in addition to cloud computing, is actually going to be extremely important in terms of how cars learn and communicate with each other. Our Snapdragon series of products focus on machine learning and computer vision on board, and as these products advance, they're going to be able to take on more and more capability in terms of fusing multiple sensors. So let's talk about 5G. So Qualcomm has been discussing 5G publicly now for over a year, and there are three key pillars in 5G that we believe change the game for the future of communications. Unlike in past technology evolutions, which were primarily focused on the phone, the 3G to 4G transition was mostly to move into smartphones and very high data rates for essentially mobile devices to connect to the cloud. With 5G, there is a bit of a difference because we have gotten to the point where we can support very high data rates with a lot of aggregation of frequency. But we believe that 5G will also be about other adjacent modes of communication, other adjacent use cases. And the automotive ecosystem has embraced this view, and we'll talk about that over the course of the session today. But we are developing 5G technology to be able to support auto-specific use cases. So mobile broadband will essentially be redefined in terms of data rates that it will be able to support. Mission-critical services will operate not at the traditional latencies of tens of milliseconds, but will be down to less than 1 millisecond for mission-critical communication. And 5G will be able to support a massive number of users in terms of the sheer number of connections needed. And all of this obviously requires significant re-architecture of the technology, and all of this will be done as a part of 3GPP standards. We are already at a point where we are now commercially seeing deployments of gigabit LTE with our X16 modems, and the first outlines of cellular V2X will come along in release 14, which we will start to do trials on later this year. But this evolution will continue over the next few years, and we will start to enter the era of 5G. So maybe to give you a bit of a sense as to what our vision looks like as far as V2X goes, we believe that communications is actually perhaps thus far overlooked, but a critical aspect of autonomous driving. In the past, when V2X services were designed and envisioned, the timing was a bit independent of the transition that has started to happen now in the industry around safety using sensors. So the autonomous driving path and V2X existed in some sense independent of each other. Today, given the advancements in communications, as well as the advancements that are taking place in the autonomous space, we believe that there is a very complementary nature in terms of the sensors that both of the paths are able to provide. In the context of communications, here are 3 examples of the various types of scenarios that autonomous driving would be able to benefit from if communications were used as a sensor. The first one is non-line of sight scenarios, obviously where if you do not have a line of sight condition, a traditional sensor is not able to capture that situation, and this is something that V2X services can do extremely well. Conveying intent in terms of being able to rely on communications rather than a traditional radar or camera sensor to judge what is going on in with the car ahead of you is a potential second scenario. And then, of course, situational awareness, being able to get a sense as to what is going on in a swarm or in a crowd of cars as an event starts to ripple through a specific traffic situation is the third. Now, all of these are possible not just through a network communication, but also direct vehicle-to-vehicle communication. And we believe that in V2X, the more endpoints that have communication, the better the quality of the end result is going to be. So V2V, cars communicating directly with each other, communicating with pedestrians and bicyclists, talking to infrastructure that is deployed on the side of the freeways or the roadways, and then, of course, talking to the network. All of these pulled together in a very low latency configuration will make a significant difference in terms of the quality of the end result. So if I look at autonomous driving and you take a look at the sensors on the left-hand side, all of which are extremely critical and in various stages of advancement in terms of the cars that we are seeing on the road today. And you combine these with communications and the dependency on communications and data that resides typically in the cloud or needs to be on the cloud because it is constantly changing. You now have a very complementary set of sensors that are improving the overall predictability and quality of autonomy. And I think as the attach rate of these technologies expand and improve, we'll be able to get to a point where autonomy will actually deliver the goals of 100% safety, zero fatality. The transition as far as the technology specs goes is somewhat as follows. The basic safety world, which is what we exist in today, is what we know as DSRC, and DSRC has had an excellent development of its own ecosystem in terms of the services, the capabilities, the use cases that have been developed as a part of the 802.11p standards. We are essentially working with a number of folks in the DSRC community. Qualcomm has products in the DSRC space, and the cellular V2X release 14 standards essentially get to the same place as DSRC does in terms of its capabilities. However, from a link budget perspective, the cellular V2X standard, which is based on LTE Advanced, offers an improvement in terms of the overall link budget, which thereby allows for much longer range and a much higher level of reliability in terms of being able to deal with the very same situation. As we move forward beyond release 14 and on to release 15 and into the 5G realm, we start to add a number of additional use cases and capabilities. Much higher throughputs come into play, higher reliability and low latency, and a much wider band of ranging and positioning. And what this allows you to basically do is add additional use cases, as you can see in the graphic on the bottom right of your slide. Technologies like being able to see through cameras that are located in cars ahead of you allows you now to be able to get a much different, much better idea of the situational awareness that is required. Platooning or cooperative driving can have not just communications, but the real-time feed of what is happening in the traffic ahead of you. And then, of course, bird's eye views or HD map updates for complex situations that are possible. So our focus on cellular V2X is to start off with release 14 and then build up a roadmap as a part of the 3GPP evolution with release 15 and beyond to add these additional capabilities. One piece that is extremely important, and I think George will talk about this in more detail in his slides, is the spectrum assignments. So today, the ITS band is what is being used for 802.11p DSRC services. We are also focused as a part of the cellular V2X efforts in the industry on the ITS band so that there can be spectrum set aside on a dedicated basis in this unlicensed band. And the basic safety services require 10 megahertz of spectrum, which is important to set aside. And then, of course, as we start to get into more advanced services in the release 14 timeframe, the goal would be to use the overall 70 megahertz or so that is set aside in 5.9 to expand over into newer safety services and newer messaging services. That's a quick overview. I will turn it over to George to get you into a little bit more technical detail on our vision towards cellular V2X.
Hi, thank you, Nakul. So this is George Tirtzis, and I'm going to get into a little bit into the cellular V2X technology and expand on some of the things Nakul already touched upon. So the path to 5G has actually already started with the release 14 V2X. The specification is going to be completed next month, and global trials are being announced and more planned globally starting later in the year. The cellular ecosystem today already enables key connected car services, including telematics, eCall, and infotainment. V2X can expand significantly the services into safety and non-safety areas. Cellular V2X brings significant improvements over 802.11p in terms of range and its ability to see through obstacles in non-line-of-sight scenarios due to its high link budget, which we'll talk about later in this discussion in more detail. By combining vehicular and cellular communications under the cellular ecosystem, it is possible to leverage one against the other for the financing of crucial roadside infrastructure. eNodeBs with their unicast and broadcast services can be combined with roadside units, RSUs, and their V2V and V2I based services. Indeed, we think there is significant value in collocating eNodeBs and RSUs in many scenarios. This, for example, will enable the network infrastructure to tap into the native language of the car, which is V2V messages broadcasted every 10 times a second by every car. And RSUs receive all these messages also. Mobile network operators can then provide more effective services via all of their cellular assets. Finally, a rich roadmap to 5G is already underway, evolving the technology to a broad range of use cases, from better situational awareness to enhanced traffic management, connected cloud services, and of course automation. CV2X defines two transmission modes that can work together to enable a broad range of automotive use cases. On the left, we have direct communications between vehicles, infrastructure, and pedestrians. This mode of operation is based on enhancements to LTE direct device-to-device communications, which were introduced in 3GPP by Qualcomm in Release 12. With the Release 14 updates, we now have a direct interface specifically designed for vehicular use cases. This interface is called PC5, and it supports the broadcast and real-time information between vehicles traveling at high speeds in high-density traffic, and even out of mobile network coverage. On the right-hand side, we have the network communication interface, leveraging existing LTE networks for wide area networking and cloud services. This utilizes what is called a UU interface, which is the interface you normally use to access the cellular networks. One significant difference between these two interfaces is that UU is an asymmetric interface with a clear infrastructure side and a client side, or UE side as it's called in 3GPP parlance. Indeed, in LTE, the uplink and downlink waveforms are different, and the MAC layer and control plane even more so. In contrast, PC5 is a symmetric interface, meaning the UE and infrastructure sides are equivalent. This is a new concept in cellular and a powerful one, which will give rise to new capabilities in terms of equipment and services. An important aspect of cellular V2X specification is its ability to operate without any dependency on the network when it's needed. This was an explicit aim from day one, and a fundamental aspect of offering a viable alternative to 802.11p as a transport, especially when it comes to safety services in 5.9 GHz band, earmarked for ITS services around the world. Indeed, when it comes to 5.9 GHz, CV2X does not require traditional wide area network credentials or SIM cards. There is no need for a subscription, and no need for an operator connection of any kind. All vehicles, infrastructure, and other road users participating in ITS services share the same frequency band and its resources. This is done in a distributed manner without any network assistance. Even synchronization can be achieved purely based on GNSS, and thus again there is no dependency on eNodeBs or other network infrastructure. The reason this is important, of course, is because we wanted to make sure that basic safety use cases are available free at the point of use to any car, whether they choose to have wide area network service or not. That's despite the fact that we believe that all cars will eventually have such wide area network services. Also, CV2X was specifically designed to work in ITS 5.9 GHz. 3GPP has been working on 5 GHz band for a while now for other reasons, but in Release 14 we introduced 5.9 GHz in 3GPP, which is now called band 47 in the terms. 5.9 GHz is of course a natural target for V2X services, as this is a well-harmonized band across most of the world, enabling economies of scale and straightforward implementations to emerge. The CV2X design took this frequency specifically into account by, for example, considering frequency-specific Doppler effects at high speeds up to 250 km per hour. And of course, while we're promoting cellular V2X in this discussion, we recognize that 802.11p technology may be deployed in some regions. Cellular V2X will coexist with 802.11p by being placed on different channels in 5.9 GHz band. Let's look now at the performance of cellular V2X. Cellular V2X has 2 times the range of A2.11p in line of sight conditions. It means you can see further, but it also means you can see more easily, meaning more reliably through obstructions. In practice, this non-line of sight performance is what matters most. This is because in a world of multiple sensors and sensor fusion, this is the most highly valued property of this new sensor, but I'll get back to this later in the talk. The range advantage comes from increased link budget. The link budget is higher in cellular V2X due to a number of advancements in technology over the last decade. The most important effects come from the 3 things identified in this slide. Longer transmission times result in more energy per bit transmitting. The waveform, which is single carrier FTM, and it is used in cellular V2X, allows more power to be pushed out through a given power amplifier. And advances in coding techniques, we're using turbo codes as opposed to convolutional codes, as well as advanced retransmission techniques allow the signal to be decodable at lower signal-to-noise ratios. We will now discuss some more tangible effects of this link budget advantage and how can this be thought of in the context of a V2X sensor that can be used with other sensors like radars and cameras. So this slide shows the traditional view of how V2X is to be used. And sure enough, cellular V2X can and will be used in such use cases. But the question is, what does this new sensor bring to the table, given that the autonomous vehicle industry is marching ahead without V2X in the mix for the time being? Indeed, the autonomous vehicle industry utilizes many other sensors to successfully navigate a number of these use cases and many more. One significant parameter here is that radar, LiDAR, cameras are all line-of-sight sensors, meaning they can only see what your eyes can see. And in fact, like the human eye, they too have their limitations and behave differently in different environments. Think of what the fog or sun reflections do to a camera. This is why sensor fusion has become such a hot topic, as by taking input from multiple sensors, one can compensate for the limitations of the others. Now, if you think of V2X as a sensor in this context, what does it bring to the system? First of all, it is a redundant sensor that will, for example, see well in a variety of environmental conditions. By this measure, is already valuable. Secondly, it is the only interactive sensor. All the other sensors are either passive or one-sided active. A camera is passively receiving light as input. Radar, on the other hand, is active as it transmits a signal, which is, however, passively bouncing off things around it. In that sense, when the driver of the car ahead of you steps on the brake, your front-facing radar needs to detect that the distance between you and the car is decreasing, and a camera might have to detect and interpret the brake light going red. Well, with V2X, the car in front is telling you it is decelerating and that the brakes have been engaged. You do not have to guess. So this is the only sensor that can deterministically tell you what another car is doing, as the cars exchange information with each other constantly. Thirdly, it is the only sensor that can tell you what an object is doing, even if the object is not in direct line of sight. I can now see the car in front of the truck ahead, or the motorbike on the other side of the car next. So now I can track the movement of cars, objects, via the vision. The ability to see cars, trucks, and hills is related to the available budget. The significance of the performance advantage of cellular V2X compared to 11p. In MWC next week, we will be demonstrating some of the CV2X use cases using a visualization system we are developing for use in trials planned for later this year. In these cases, we are simulating cellular V2X and 11p communications using standard to predict communications in line of sight and non-line of sight conditions. We then apply these models to practical use cases like the ones in the slide to see how it would perform. Let's see a couple of examples here. One of these is a non-line of sight case in which there is a stopped car at the blind curve. When we make the demo public after MWC, you see there is a hill on the curve. obstructing the car on the other side of it. So the driver of our car can see the obstruction until he sees coming out of the car and very close to it. In this simulation, we predict the range to be around 60 meters for A2.11p and just under 110 meters for cellular V2X due to the existence of the obstructing hill. These ranges sound low, but this is the effect of an obstruction can have, and this is where the value of link budget advantage comes apparent. Now, one can think of obstructions that absorb more or less energy, but the overall behavior remains. The curves on the right side of the slide show stopping distance calculations. In other words, how many meters in the y-axis it takes to stop depending on how fast you are going in miles per hour on the x-axis. These curves are drawn according to established techniques defined in the well-known Green Book, while they are consistent also with the camped acceleration model. So what you can see on the curves is that under normal road conditions, if you get a warning 60 meters away from the obstruction, you will be able to stop or maneuver safely as long as your speed is no more than 46 miles per hour. That's almost 75 kilometers. Cellular V2X longer range in this case allows a car to go as fast as 63 miles per hour, which is just over 100 kilometers per hour. But that is an unlikely speed at a narrow signaling road we are trying this out. So one could say that both technologies satisfy this use case. If you, however, consider an icy road where it can take a lot longer to stop a car, you see that even this rather straightforward use case can become challenging with 11p, providing warnings at safe distance only up to 28 miles per hour, 45 kilometers per hour, while CV2X does so up to 39 miles per hour, which is over 60 kilometers per hour. Now let's look at a line of sight scenario, such as a do not pass warning use case, where long range matters more. In this case, our driver is behind the truck and wants to overtake it. A third car is coming in the opposite direction. The question is, how far does the third car in the opposite direction have to be at a given speed so that our driver can perform the maneuver safely? And if the third car is not far enough, can V2X technology provide a do not pass warning to the driver? Now, one can calculate the distance needed between the two cars at any given speed, again based on the Green Book. This is represented by the sloping green line on the curve on the right. The vertical lines represent the CV2X range, 443 meters, and A2.11p range, 240 meters, according to our model in line-of-sight conditions. The point at which the curved line crosses the two range lines indicates the maximum speed at which the two cars can be going and still perform the maneuver safely. This speed is 28 miles per hour, or 45 kilometers for A2.11p, and a more reasonable 43 miles per hour, or around 70 kilometers per hour for CV2X. These numbers are somewhat conservative for both technologies, but again, the purpose is to show the overall behavior. So both of these use cases will be part of the demo in the MWC next week, and hopefully we'll make the video of that available right after that. Now, to wrap up this section, I want to make a couple more high-level points. Firstly, returning to the technology itself, I want to make a point regarding upper layers. Cellular V2X aims to provide a modern transport layer alternative to A2.11p, with superior performance and a clear evolution path, which can benefit from the introduction of 5G technologies and the cellular ecosystem as a whole. In that sense, we are explicitly reusing all the upper layers that have been defined for over a decade now in ISO, ETSI, and IEEE. A very rich set of applications and services has also been defined by the automotive industry, for example, by the Society of Automotive Engineers. Reusing all this is critical to our ability to commercialize the technology quickly and safely, as most of the work that has been done over the last decade in this area is indeed in these upper layers rather than the transport layer itself. Finally, I want to place CV2X back in the overall architecture we envision. Cellular V2X allows vehicles to use PC5 for V2V, V2I, V2P services free at the point of use, utilizing the common 5.9 GHz band. It allows more advanced connected vehicles and other connected road users to combine PC5 with UU wide area network connectivity to get access to more advanced services. It indeed enables infrastructure vendors and mobile network operators to provide and manage equipment supporting both UU and PC5 interfaces. In that way, for example, the mobile network operator can manage the wireless roadside systems, including RSUs. It can then offer a service across its network to road operators who can interconnect their traffic lights and digital signs without having to become wireless experts themselves or know how to manage vast numbers of wireless equipment, something the cellular ecosystem knows very well how to do. So this is it for me, and the next section you will see how the technology will evolve and how the ecosystem around it is emerging. It's Nakul is going to take you through.
Thank you, George. So that was a very comprehensive, brief, but comprehensive overview of the technical piece. Let me give you a bit of an idea as to the level of interest that the industry is showing in the cellular V2X space. So the 5G AA was formed in September of 2016, and over the last 5 months or so, we have now seen almost 40 members representing various facets of the industry, of course automakers, but also operators, infrastructure vendors, test equipment manufacturers, tier 1 suppliers have all become part of this new ecosystem. Now the 5G AA is probably one of the first organizations really in the industry that spans the interests of the automotive industry very specifically around telecommunications and wireless evolution. The assumptions here are that 3GPP is where most of the standards work is done, and 5G AA then influences 3GPP, takes from 3GPP and creates working groups, creates technology trials, use case development, and other related activities to ensure that the interests of the automotive community are taken care of. So this is what I was referring to earlier in my comments around how 5G is a little bit different than what we have seen in the past. We will be demonstrating at Mobile World Congress an early simulation of our cellular V2X trial platforms that George was referring to. But really the main point here is that starting the second half of 2017, we will actually have field trials in various parts of the world kicking off. We've announced a trial in the German A9 corridor with Audi, Ericsson, Swarco, and the University of Kaiserslautern. This was announced at CES, and we will have additional announcements coming up over the coming weeks, but really our focus is to make sure that the technology is visible and made available to start off with trials really all over the world. So I think the one question that we get asked quite a bit is really around the economics of cellular V2X. And really the premise that 5G AA was built on, the premise around cellular V2X technology fundamentally is we are seeing the attach rate of communications in the car move higher up very quickly. And this initially started off as being something that was focused on telematics, on over-the-air updates, but really the fundamental nature of how cars are being designed and architected necessitates the need to have a dedicated wireless connection in the car. Our roadmaps going forward are going to focus on making sure that the modems that we are putting into vehicles that are talking to the cloud, to the network, those same modems have the ability to also support vehicle-to-vehicle communication. So from an overall system cost perspective, we are very focused on making sure that the level of integration is very high to ensure that the burden on the automaker and the end consumer is minimized. From a deployment perspective, George touched on this in his remarks. We believe that to be able to take advantage of V2X, you really need a ubiquitous global footprint of deployment. And the cost of deployment, when shared with the larger deployment around technologies like LTE Advanced and 5G, will definitely make a big difference in terms of the success of V2X. So there is a lot of interest not only from infrastructure vendors and operators, but also roadside service unit providers and operators that are involved in ensuring that transportation networks are intelligent. The next generation of transportation networks and infrastructure that is deployed will be designed to be friendly towards automobiles for purposes of autonomous driving, for purposes of V2X services. And so the cost of deployment will actually be an extremely important facet. The third aspect, of course, is there is a huge ecosystem in the mobile world that has a lot of expertise across a variety of different wireless technologies. As we start to see the deployment of 5G take off, we will essentially see band deployments that have never been seen before. We're talking about millimeter wave being deployed in very high bands. Of course, in the sub-6 gigahertz, there'll be plenty of deployment. So there is a huge amount of expertise that exists in the ecosystem that will be applied to V2X services. And then finally, all of this is going to result in new business opportunities, new economies of scale, new services opportunities that I think is going to make the car a very important aspect of the wireless networks of the future. To give you an idea as to what the roadmap looks like, we have seen advances in LTE on an annual basis really since the beginning of this decade. We here at Qualcomm are on our 6th generation of commercial deployment of modem silicon here in 2017, and LTE really started off in earnest in 2010, 2011. So the pace at which wireless technology is moving is extremely rapid. And a number of different services that you are seeing on the slide really point to how not only is there innovation going on in higher speed mobile broadband services, but there is a lot of innovation going on in terms of how to use spectrum more efficiently, how to introduce services such as broadcast to be able to support differentiators for IoT type services, especially for broader and more extended ranges. And then, of course, from a safety perspective, a number of different ultra-low latency services are going to come in. So this advancement has started off already. We are in release 13 today, and by the end of this year, we will, like I was mentioning earlier, have trials on release 14 with cellular V2X kicked off. As we start to migrate towards 5G NR, which will be in the release 15 and release 16 timeframe, the ecosystem will continue to add more capabilities to build off of what has been created on the cellular V2X platform, such that the key differentiators of 5G from a latency perspective, from a much higher data rate perspective, are taken advantage of. So our vision is that there is a tremendous amount of innovation that is going on in the industry today as far as autonomous driving goes. Camera technology, radar technology, LiDAR, high-definition maps, the fusing of all of these sensors, the machine learning and deep learning algorithms that are powering all of these different innovations are ongoing. And V2X brings along with it a completely complementary and highly deterministic and predictable sensor that will improve the quality of the overall outcome. And it can be deployed globally. It has support from the entire diverse ecosystem of automakers, tier 1 suppliers, operators, silicon providers, infra vendors. It will have the right characteristics in terms of the high throughput, the low latency, the ultra-high reliability and security. And I think very importantly, it will have a roadmap that is going to be tied to the fundamental foundation of the wireless ecosystem evolution that will ensure that communications remains a central part of the automotive architecture evolution. So I'd like to end with the slide that I started off with. We believe that this is a time like no other in the history of the automobile, and the car is becoming a citizen of the internet, a citizen of the cloud, and there is a tremendous amount of technology, both from a connectivity perspective and a computation perspective, that is entering the car. But from our perspective, the communications piece creates an opportunity like none other, allowing cars to be able to communicate with each other and its surroundings, including humans, including infrastructure, will create a safer and more intelligent environment for the auto industry.
Great. Thank you so much. This is Tara Seals back with you. And with that, we will move to the Q&A. Just as a reminder, there's still time to submit your questions using the button on the lower left corner of your screen there. We have lots of great questions already, and we'll try to get to as many as possible. And with that, let's go to the first one. Here's a question. What frequencies will cellular V2X work on?
So I can take that real quick. So currently the trials that we are planning to operate at are in the 5.9 gigahertz. And that's the ITS band that has been set aside for V2X services. So that's where the focus is currently.
Gotcha. Okay, great. Thanks. Okay, and also, what is Qualcomm's view on the coexistence of 802.11p and V2X based on LTE?
George, would you like to take that?
Yeah. So, as we mentioned in the slides, we think the two technologies can coexist. There is obviously within their advantages to go with cellular V2X, but the technologies can coexist in 5.9 gigahertz if they are placed on different channels. There are 7 channels, 10 megahertz channels in that band, and there is space for both from that perspective. But we think also it's important to consider future services and reserve space for or look at this common band in this context and limit the use of the spectrum to what is necessary for the day one safety use cases that are important to get on the road, and then allow the spectrum also to be used for more advanced services with the evolution we expect of the technology.
Great. Okay, and since some autonomous vehicles aren't going to be connected to the cloud, what is the business case for adding connectivity in that case?
So, I think the trends that we are starting to see in the industry are that by definition cars are going to have connectivity to the cloud. The question is the car always in an environment where there is coverage or connectivity back up to the cellular network or the wireless network? Now, in the case of V2X, just answering the question very specifically, the technology is designed for car-to-car communication without the need to actually have a connection back to the cloud. So given the fact that there is a significant increase in the auto industry to equip all cars with modems, not just for the sake of keeping the car updated, but also in some parts of the world because of mandates, and given that V2X will be mostly V2B focused, I think the business case is actually extremely strong. Great.
We also have a question about using the existing 4G networks to support some of these use cases. The question is, wouldn't using the 4G network be the fastest way to start supporting some of these while 5G and other network evolutions are being worked out?
Yeah, so of course 4G networks support vehicular use cases today. But if you see the focus on a lot of the V2X use cases has to do with communication between cars that are near you and cars that are maybe they have wide area connectivity, they don't have wide connectivity, or they are connected through different operator services. So that is the what V2X brings, and particularly V2V, to the picture. It brings a common standard and a common way to talk between cars in proximity. By the way, if you are going to have use cases that care about latency, the fastest way to talk to a car next to you is directly. That's always going to be the case, and that at in some cases is important to have that low latency. So yes, so some things will be done over the network, but this brings a significant new capability to the ecosystem.
Okay, great. And just as a follow-on to that, when it comes to 5G V2X, will that be backward compatible, do you anticipate?
Yes. So the way that cellular evolution works is that we are definitely looking at forwards compatibility as well as backwards compatibility. So the plan already that is being formed in 3GPP is taking into account of evolving services within 5.9 gigahertz band in a forward compatible way.
Okay, great. What type of safety applications are you looking to support through the network?
So there are a large number of safety applications. I think these are very well understood broadly in the DSRC space as well. But like was mentioned in the slides, I think basic applications such as forward collision warning, do not pass warning, etc., are what can be supported through direct vehicle-to-vehicle communication. But in addition, there are use cases that get into blind intersections where the need for a roadside unit in the infrastructure could be taken advantage of. Or there could also be applications that allow you to be able to get context-specific information around hazards or weather or traffic scenarios in a specific area that involve the V2N piece. There are, of course, V2P applications where pedestrians may be involved, where communication between a smartphone and a car is actually something that we can look at. So it's a very large number of safety use cases.
Okay. And when will Qualcomm offer support for cellular V2X and Snapdragon automotive processors and modems? So
we are in the process of getting into field trials in the second half of 2017. And based upon the results of those trials and based upon the feedback from customers, we plan to build out a roadmap that will include V2X capability across our entire portfolio of products. We can definitely have specific discussions on a case-by-case basis.
And here's a question that follows up on a couple of the themes that you already talked about in the Q&A. How open are OEMs to accepting the cellular V2X systems, first of all? And another part of this question is what about the coexistence with 802.11p and ITS bands? Along with, is the 70 megahertz enough to support ITS use cases when 5G is promising?
Let me take the first one, and I'll hand it off to George for the second one. So, like I mentioned earlier, we were part of the founding team for 5G AA only in September of 2016, and there has been tremendous interest in this industry association. And We believe the main reason is that not only is communications becoming central to the architecture of a car, but automakers are very interested in making sure that their requirements, their use cases, their forward planning is considered as next generation technologies in the wireless space are developed. So from that perspective, I think there's a lot of receptivity within the automotive ecosystem around cellular V2X. Now, getting to specifics, I think what this really comes down to is, if you think about the cost of enabling communications inside a car and the cost of enabling the ecosystem, the infrastructure, the global ubiquitous deployment, all of those costs require a very strong ecosystem to be able to get this technology to be deployed at scale. So one of the reasons why a number of automakers are looking at cellular V2X very seriously is that it does offer the ability for the technology to scale very quickly, because the modem technology is already being fitted into vehicles, and the ecosystem that has to go support this at scale is a large ecosystem that has a very tight tie-in into overall wireless deployment evolution. And George, I'll turn it to you for the coexistence in the 70 megahertz question.
So the coexistence, I think we covered. We talked about the two technologies being placed in different channels in 5.9 gigahertz band. On 70 gigahertz, there is, I'm not aware of anything available for vehicular communications at 70. There is 63, 64 gigahertz in Europe that has been discussed, and that is an interesting complementary channel. And I say complementary because, of course, now you are in millimeter wave frequencies, and there are where the range that you can expect is a lot shorter. So there is utility because there is a lot of bandwidth that can be used for some advanced sensor sharing, ranging style use cases, but at the expense of very short range. Also, it's not very well unified, harmonized across the world. So it's only available right now in Europe. So that's the situation of that frequency.
Okay, great. Thank you. We have a sort of practicality question here. How do we bridge the time when only some cars are supporting V2X types of communications? In specific, this person would like to know what happens if a car comes his or her way that does not support V2X services. Is crashing a possibility, and what can prevent that?
I think it's a very good question. And I think it's a question of attach rate and this is really a question that applies to any kind of scenario where you have to rely on other points in the cloud to also have the same capability as you do. And this is really going to get solved over a period of time. But what we are starting to see actually in terms of the interest is because cars are getting fitted with modem technology pretty much at a very high rate in most parts of the world. And we also are looking very closely at how to enable V2P capability, as in put the same V2X technology inside handsets. The idea is to be able to get to a very high level of reliance on a communication sensor based upon the number of devices, the number of endpoints that actually are enabled with the technology. But the question is very accurate. It will be a period of time up until you can rely on every device or every car around you to actually be enabled with the technology. So this will be a complementary sensor, as has been shared several times, and the use cases will have to be very specific to the ones that have a very high level of predictability in terms of where you can rely on vehicle-to-vehicle communications.
Mm-hmm. Okay, gotcha. And another practical question, how much would a modern vehicle increase in terms of sticker price to support this basic functionality, just on average, ballpark figure?
Yeah, so I'll answer this a bit differently. I think if you think about the way wireless technology has been fitted into vehicles over the last 10 years or so, it was really something that was what I would call, it was shoehorned into the overall vehicle architecture. The car architecture was never really designed to take full advantage of everything that wireless technology could bring. Some simple examples. The ability to be able to get 4x4 MIMO and much higher data rates is limited because the car antenna architecture would require to be overhauled for taking full advantage of the wireless capability. What's going on now as we start to look at LTE Advanced in 5G is that automakers are looking very closely at how the overall car architecture has to change with the number of antennas that go into vehicles, from Wi-Fi to Bluetooth to V2X to multiple 5G antennas, tuner antennas. So there is an opportunity to be able to overhaul the overall communications backplane of the car, so to say. From a cost perspective, the level of integration that is happening in silicon nowadays is so high. So for us, the cost aspect in terms of adding V2X over a period of time, it will just get absorbed into the overall cost of modem technology. The cost usually is much higher when you have to have a dedicated new system that you have to deploy in the vehicles for new technology, and usually that happens for the first few years when the attach rate is not high. But as soon as the attach rate starts to get to a mandate level or extremely high, the focus is on integrating, and that's what at Qualcomm our intent is to do.
Okay, great. We just have time for a couple more here, so let me ask you this. Who do you see that would be operating all the V2I equipment by the roadside? Are these operators, highway agencies, another entity?
I think it's a very good question, and the answer probably varies on a geography basis, but I think it would be a combination of operators, highway agencies. In some parts of the world, this could be something that could be part of the overall transportation network that is deployed by the government. So I would say it would normally be a combination of a public-private partnership. In a number of cases, it would be existing roadside operators or even regular wireless operators.
Mm-hmm. Okay, great. And this is our last question. So just like to say to the audience, we've had a lot of great questions today. We couldn't get to them all. But our speakers will be getting back to everyone who submitted a question personally after the webinar. So to wrap things up, let me ask, the current cell sites have limitations for dense areas. So in order to make this work, will you need to deploy microcells and other types of access to prevent congestion?
Yeah, if I can take this one. It's a good question. So the densification, as it's called, of the network is happening as a matter of course. As more and more devices get connected and applications have higher demand for throughput and low latencies, all the networks are getting more and more densified, meaning there are more E-Node-B small cells, microcells being deployed wherever they are needed in dense areas. And this is where actually the combination of this traditional cellular equipment with roadside infrastructure using V2X technology and the PC5 interface is very appealing, because then you can combine the functionality. You have an RSU with PC5 that can essentially participate in all the V2V communications and receive all the regular V2V messages sent by cars. And then at the same area, you have the cellular infrastructure that can provide services as needed to the same cars. And that combination is very powerful. And I think it's happening naturally, and it only needs to be combined now with V2X and traditional LTE. So it's a very interesting thing to watch how it will happen.
Okay, great. And that'll wrap it up for today. I'd like to thank everybody for attending our Fierce Markets webinar and submitting so many great questions. I'd also like to thank our speakers, Nicole and George, for participating, and thanks to Qualcomm for presenting it. Just as one more reminder, the webinar has been recorded, so you'll be able to access it within about 24 hours just using the same page that you used to register. And also you can download the slides using the button on the left-hand side of the screen. So I'm Tara Seals. Thank you very much again for joining, and we look forward to seeing you at future events.